All right, guys, so hope you're keeping safe at home. And I'm making some videos for you guys. Today is Tuesday, so today I'm still at school. We're required to come to school and to make some planning for this 4 weeks when you guys are at home. So obviously these 4 weeks, 2 weeks are holiday, so 2 weeks are when you guys are supposed to be working. So, but nonetheless, I don't care which day you're working or you're not working. So I'm making all these videos and lessons all together so that when you're at home and you can just study at your own pace and then whenever you're free. Okay, so yeah, so. Don't be overwhelmed by all the lessons. Now, we all of a sudden got a lot of lessons, or not so many lessons, because sometimes, like you know, in class, sometimes we have one lesson, and then, well, even though it looks like only 5 lessons, but it actually requires 10 lessons to get it done because a lot of the questions could be difficult. So you might need some help. So if you need any help, like just send me an email. If there's any particular question you want to talk about, I'll talk about the important ones, and I'm also going to give out the answers for the booklet. And obviously, if you have the textbook, then you got the answers for the textbook as well on the back. If there's any particular question you want me to talk about, so send me email, and then I can make a video of it, or I can just explain. If it's a small question, I might just explain it to you if I think it will be beneficial for everyone, so I might make a video for everyone. I actually have a whiteboard at home as well, so I will be making videos at home as well. Okay, all right, sweet. So without further ado, today we're gonna look at angular momentum. Okay, so same with linear momentum. Angular momentum is a concept that we developed in order to help us to explain situations. Okay, so as you've learned now, is all the rotational quantity can come from the linear quantity, and all the rotational equation and basically come from the linear equation as well. So all the concepts inside are exactly the same, just we're changing linear to rotational. Okay, all right, so now without further ado, let's have a look. What is the linear momentum? Linear momentum was defined P equals mv, right? So momentum equals to mass times velocity, okay? And then what is rotational momentum or angular momentum? Angular momentum is L equals to, instead of m, now I have rotational inertia, which is I. And then time, instead of speed, now I have rotational speed, or called angular speed, so which is gonna be omega, okay? And remember the word we're using is angular, okay? And then now let's have a look of the unit. Well, we got momentum unit. Momentum unit is, we just use the equation, come from kg, mass is kg, and then speed is meter per second. So it's gonna be speed kg meter per second, right? Okay, so let's have a look at the angular momentum. What is the angular momentum one? Well, it's gonna be I's unit times omega's unit, right? All right, so which is gonna be this? Well, we've learned what is I. We got mr squared. That is the typical equation for I. So the unit was kg meter squared. That was my unit for I. Or then what is omega? Omega is the angular speed, which is rad per second, right? Okay, so rad, what is rad? And I've explained it before. Rad is actually just a ratio, because omega equal to theta divided by time. Well, what is theta? Theta is equal to the distance divided by the radius. Well, both of these are meter. So this meter divided by the meter, we call it the rad, which is actually just ratio. So it actually is just nothing. It's just it doesn't really have a unit. Rad is actually just nothing, okay? It's just this ratio. Okay, so now we can say, well, meter divided by second. So meter divided by meter, then together divided by second. Actually, it's just 1/2. So this is the reason why, instead of saying rad per second, we can pretty much just ignore the rad. Obviously, if you talk about angular speed, you should still use omega, still use rad per second. But in this circumstances, you can actually just cancel the rad. So then we will get the unit for L. So what is the unit for L? It's actually just kg meter squared. So rad per second, we can just cancel the rad, say it's kg meter squared per second. Or another way of writing it, obviously, is kg meter squared second to the power of -1. Now that's how I can get a unit for L. Okay, and then there's another method to do it, which I'll explain later as well. Okay, so well, to calculate angular momentum, then it's easy. Well, once you find I, once you find omega, and then you can times them together, you get L. Okay, so that's not very difficult. Okay, and then the next part is there is another equation. This equation is this. It's L equal to mvr. Obviously, these equations are all going to be given to you, so I'm going to highlight here. Okay, and then, well, how did I get this equation, and when does this equation apply? So this applies to this situation. So if you got a thing that's going under circular motion, okay? If it's going under circular motion, there will be angular momentum as well, because this thing rotating, it just keeps wanting to rotate like that. Well, then what do we have? We got this. So L equals to I omega, right? So which is applying to all situations. And then in this situation, we've learned that I equals to mr squared. Okay, so that is my equation, and then we can put this to there to replace it. So now L is going to equal to mr squared omega. Right? Okay, and then what is omega? I can replace omega using this. So mr squared, omega equal to the linear speed divided by r. So now this becomes linear speed divided by r. And then I can cancel this r and this over here. Now I got mvr. Okay, so let's have a look. What is this m? M is the little mass over here. And then what is this v? It's the tangential speed or the circular speed this object has. And then what is the r? R is the radius over here. So now if you time these three quantities here together, then you will get the rotational momentum of this circular thing. So a typical question was in your question, say something called a merry-go-round. Is if you have a merry-go-round, there's a thing over here, right? That's what the kids play thing, and then you're running, and then you jump onto it. So when you're running as a person going in a circle, you got an angular speed, and that angular momentum can be calculated by using this equation. Okay, and obviously because of this equation also applies to a situation where you have say a hollow ring like this. If you got a hollow ring like this, the mass is on the outside over here. So basically you can ignore the thickness over here. If you can ignore the thickness, then you will have an R over here as well. So L equal to mvr will still apply to this. That is because I equal to mr squared will still apply to this situation. Okay, so if you have a ball or other situation, maybe you will have half mr squared, so the equation will become L equals to half mvr. So, but that's not important. So what's important is you need to know that, okay, we've got two equations here. This one applies to all situations, and then this one only applies to this specific situation where it's a circular motion of a point mass or it's a hollow ring kind of situation. Okay. All right. So once we know how to calculate them, then it becomes easy. So we're going to use this for the next part, which is going to be conservation of angular momentum. Okay. So which we will talk about it in the next video. So go home, have a try of this topic. So there are some questions in your book. So angular momentum, and have a try of the homeworks over here for angular momentum. And then once you feel confident of that, and then we're gonna move on to conservation of angular momentum. Okay, see you in the next video. Stay safe.